Hi everyone. Today a video on aromatic chemistry, and we're going to be looking into an introduction into it, naming physical properties and reactivity. So what are arenes? Arenes are hydrocarbons that are based on benzene. Benzene is C6H6. It's shown in the middle here, either as this hexagon with a ring in the middle, or actually writing out the carbons and hydrogens, so not a skeletal formula as shown on the left, but actually drawing out the displayed formula with alternating double and single bonds. And benzene is the simplest arene. It's a hexagonal ring structure with a special type of bonding. And although it's it's unsaturated, doesn't have the maximum number of carbon-hydrogen bonds it can have, like alkenes, it's very stable. And so benzene and other arenes have some characteristic properties. Now, the first person to come along with this idea of what benzene looked like was a guy called Kekulé. And he originally proposed that benzene was a cyclic molecule with alternating single and double bonds. He had this dream of a snake biting its own tail to make a cyclic molecule. However, this left some questions still unanswered. If you had a cyclic triene, like we've shown of that structure in the middle, if we've shown it on the right here with the alternating single and double bonds, it should show addition reactions, electrophilic addition reactions like ethene does, like alkenes do, but benzene rarely does. Kekulé's structure should also give rise to isomeric substituted compounds, disubstituted compounds. The idea being that the double bonds can either be in alternating positions, as we've shown there with that what we call a resonance arrow, a double-ended arrow. The double bonds can be essentially between either sets of two carbon atoms. So there should be two isomers of it, and there wasn't. And also that the hexagon shouldn't be completely symmetrical. Remember that double bonds are shorter and stronger than single bonds, and so the carbon-carbon double bonds should be shorter in length than the carbon-carbon single bonds, which should be longer in length. Now we can use a technique called X-ray diffraction to actually see the shape of these molecules, and as you can see from that sort of X-ray diffraction image at the bottom here, every single bond length is exactly the same. It's a perfectly symmetrical hexagon. So this implies that every single bond length and bond strength is the same. So Kekulé suggested that benzene consisted of these two structures in rapid equilibrium. And this idea was further then developed into the idea of what we call resonance between two structures. The structure that we see on the left, which has the hexagon with a circle in the middle, is the true resonance hybrid structure. That is the structure that actually exists of benzene. And what we can say is that it's a weighted average of the two sort of localized structures, what we call canonical forms. These are the benzene that we've shown there with the alternating single and double bonds. Now, neither of those two structures actually exist. It doesn't actually exist as one of those or the other. The actual structure is the weighted average of those, that ring, the hexagon with the ring. And this idea of resonance is that both of these structures contribute to it. It's a weighted average, but neither of those canonical forms actually exist. And this weighted average, the benzene with the circling, is a more stable molecule than either of those canonical forms. So looking into the bonding and structure of benzene, we said that benzene doesn't really undergo addition reactions, despite it being an unsaturated molecule. So it's not like having bromine addition to alkenes, an electrophilic addition reaction. It rarely undergoes that. And as we saw from the X-ray diffraction image, all of the carbon bond lengths are exactly the same length. And also, if we take an NMR of benzene, all of the hydrogen atoms are in exactly the same environment. They're all equivalent. And if we do a carbon NMR, all of the carbons are in exactly the same environment. They're equivalent. So benzene is a planar hexagon of cyclic carbon atoms. And each of these carbon atoms is bonded to two other carbon atoms and bonded to one hydrogen. And so the bond angles are all 120 degrees. And all of the bond lengths, as we saw from that X-ray diffraction image, are exactly the same. As you can see from that image on the right, the carbon-carbon bond length of 139 picometers. Now this length is intermediate between a carbon-carbon single bond, which has a length of 154 picometers, and a carbon-carbon double bond of 134 picometers. So we can think of each carbon-carbon bond as being in between a single and a double bond. Think of it as a kind of 1.5 type bond. This is why we use that delocalized circle representation. We don't represent it as a double bond and a single bond and a double bond in that localized structure, because that's not technically correct. There isn't some that are shorter and some that are longer. Everything has this intermediate 1.5 carbon-carbon bond length. And so that's why we use that delocalized circle representation. And so this idea can be explained through something called electron delocalization. This is where our electrons are spread out over more than 2 atoms. And in this case, the electrons get spread over all 6 of the carbon atoms that make up the ring. So if we consider each carbon atom, it has 3 covalent bonds. It has 2 covalent bonds to carbon atoms, either side of it, and it has a covalent bond to a hydrogen. Now what this means is it has 1 p orbital, like in an alkene, where we have 3 single bonds and 1 p orbital that is left free with an electron in. If we think about our pi bond forming in ethene, we have an electron in a p orbital, a free p orbital in each carbon. These combine together to give a delocalized pi orbital across both atoms. A similar thing happens in benzene, just to a greater extent, because there's now 6 carbon atoms, not just 2. And so there are 6 carbon atoms, all that have a p orbital with an electron in, the 4th electron from carbon in it. And these p orbitals are what we call perpendicular to the plane of the ring. So the ring is planar, is flat, and these p orbitals are at right angles to the plane of that ring. And so this is a requirement for them to be able to do this and to be able to communicate and produce aromaticity. These p orbitals need to be all in the same plane as each other, and they need to be able to communicate. They need to be able to essentially sort of see each other. And so these p orbitals can overlap with each other, and they can cause the electrons to become delocalized. They're now no longer associated with just one carbon atom or even just a carbon-carbon bond like in an alkene, but they are completely delocalized around that entire benzene ring. And so like in an alkene, where we have our pi bond having a region of electron density above and below the carbon-carbon bond, in ethene, for example, in benzene, we now have this delocalized region of electron density above and below the plane of the ring. It's a delocalized pi system. And this is what gives rise to something called aromatic stability. It's the reason why this doesn't undergo addition reactions like we see in alkenes with bromine or HBr, for example. Because if it did, it would break this huge delocalization. That's a massive energy penalty. Now, something that isn't examinable but is very interesting to note is that we draw both cyclohexane, the completely saturated version of benzene, if you like, and benzene as exactly the same sort of structure. We draw it as a flat hexagon. In reality, the structures are very, very different. So benzene, as we said, is a perfectly flat planar molecule. And the reason it's perfectly flat is because we want these p orbitals to be able to communicate. If the hexagon was sort of had lots of bends and kinks in it, then it wouldn't actually allow these p orbitals to be able to see each other and be able to communicate as effectively, and we wouldn't get that delocalization. Cyclohexane doesn't need to have this requirement, right? We have a saturated system, we have 4 covalent bonds per carbon, we don't have any empty p orbitals that can be used, and so actually the structure of cyclohexane in 3D, it adopts this what we call a chair conformation. It isn't a perfectly flat hexagon. In fact, it is kind of sort of bent. And the reason why it adopts this structure, while that structure may look a bit less nice to look at, the reason it adopts that structure is because in doing so, all of the bond angles are much, much closer to the perfect kind of 109.5 degree angle we want for a tetrahedral system. It's much closer than it would be if you work out what the angle is on the interior of a hexagon compared to the perfect 109 degree angle that we get from the chair conformation. That's the reason why the chair conformation is favoured, because the angles are much closer to that 109.5 degree that we want for a tetrahedral system. So we've said that aromatic compounds are very, very stable, and we can look at a couple of pieces of evidence for stability of them. We've already said that they don't undergo this kind of addition reactions that we've seen with alkenes, despite being unsaturated. But one of the main pieces of evidence for stability is through thermodynamic data, through measuring the enthalpy change of hydrogenation. So we can take cyclohexene just with one double bond, and we can measure the enthalpy of hydrogenation, so to add hydrogen across that double bond and to completely saturate the molecule. And it turns out that the enthalpy change for this is negative 120 kilojoules per mole. It's exothermic because we're forming bonds, right? We're forming bonds from carbon to hydrogen. Now, we can then take this further and we can look at the hydrogenation of cyclohexane-2,4-diene. So now having two double bonds. Now you'd expect that if one double bond was negative 120, that two double bonds would just be twice the amount. Now actually it's just slightly less. The enthalpy change for that two double bond system is negative 232. So it's 8 kilojoules per mole more stable than you'd expect for the 240 kilojoule per mole value. And the reason this comes about is because of something called resonance stabilization energy. This idea that these double bonds can kind of move about. They don't necessarily have to be on those two carbon atoms, they can move about elsewhere. And this then extends to doing the sort of hypothetical molecule, cyclohexane-1,3,5-triene. Remember that doesn't actually exist. Benzene with the delocalized system is the thing that exists. Theoretically, it should be 3 times the value of cyclohexene. It should be 360 kilojoules per mole. The actual enthalpy change is minus 208 kilojoules per mole. So it's a massive 152 kilojoules per mole more stable than expected. And that stability is due to the delocalization of the electrons, the aromatic stability. That's what makes it so stable, that these electrons can delocalize across multiple carbon atoms. So in terms of physical properties, benzene's a colorless liquid at room temperature. It boils at 353 Kelvin and it freezes at room temperature, essentially 298 Kelvin. And so the boiling point is comparable to that of hexane, another 6-carbon molecule, but the melting point is much, much higher than hexane's because it packs together much, much more effectively in the solid state. You can imagine that trying to pack together the hexane chains, which are kind of zigzag chains, can be a bit more difficult than just packing very, very flat planar hexagons on top of each other. And so because they pack together more effectively, the van der Waals forces between them are stronger. There's also what we call pi stacking. The pi systems can interact with each other, and so it takes much more energy to melt. Now, like other non-polar hydrocarbons, because they're non-polar, they don't like to mix with water or any other polar solvent, but they do mix well with non-polar solvents, this idea of like dissolves like. So the non-polar hydrocarbon dissolves up quite well in a non-polar solvent. And the key thing is that you don't really want to be handling benzene because benzene is carcinogenic. Now, when it comes to naming aromatic compounds, typically, if they're substituted, obviously if it's just the one we've been seeing, it's named as benzene. But substituted arenes are normally named as a derivative of benzene. So benzene essentially becomes the suffix of the name, it becomes the root of the name. So if we have a chlorine attached, we call that chlorobenzene. If we have a nitro group attached to an NO2 group, that's very important, we'll see in the next video, this is nitrobenzene. If we have an alkyl chain, for example an ethyl chain attached, this is ethylbenzene. And the normal IUPAC rules apply for naming it. So if we've got these substituents, if we have multiple of them, we have to use di, tri, tetra terminology. If there's different substituents, we have to number their position relative to each other. We always want the lowest numbers possible. And remember that we name everything in terms of alphabetical order, not numerical. Now, sometimes the substituent is included in the root of the name. So this is important for benzoic acid or for benzaldehyde. So carboxylic acids have the kind of highest priority in naming, followed by derivatives such as aldehydes. And so these are named slightly differently. And there's different names for them. There's sometimes non-systematic names used for common derivatives as well. So you might see benzoic acid being used for benzene carboxylic acid. You might see benzaldehyde being used for benzene carbaldehyde, but they mean the same thing. Sometimes we name it slightly differently as well. So that's the C6H5 group, essentially a benzene ring being bonded to something, is known as a phenol group. You might see it sometimes in structures being sort of shorthanded to PH, to denote a phenol group. And sometimes this is used for naming purposes. So the benzene ring is considered the substituent rather than the root of the name. So examples of this would be where we have a benzene with an alcohol group attached. This is named as phenol. So we use the suffix ol for the alcohol, and the phen comes from phenol. Or if we have an amine group attached, remember the suffix amine is used for that, and so this is phenylamine, or the non-systematic name of that is aniline. And so the reactivity of aromatic compounds, we'll see in a lot more detail in the next video in this series and look at the mechanism for it. But the ring is a very, very strong region of electron density. We have these delocalized pi bonds, essentially these 6 carbon atoms that have all delocalized their electrons, and we have this delocalized pi system above and below the plane of the ring. So it's very electron rich, high electron density. And so therefore it's very good at acting as a nucleophile, and it can be attacked by electrophiles. Remember that a nucleophile is an electron pair donor, a electrophile is an electron pair acceptor. This tends to be positive ions or positive ends of dipoles, delta positive atoms. And the aromatic ring is very, very stable. It needs a very large input of energy to be able to break that delocalized bonding and break the ring. Remember, we saw that delocalization energy a couple of slides ago, at 152 kilojoules per mole. It's really, really stable, and it means that typically the ring always remains intact in the reactions of arenes. It doesn't mean that we can't break the ring temporarily, but we always end up reforming that aromaticity because it's such an energy gain, it's such a stable compound to have this aromatic delocalization. And so most of the reactions of aromatic systems are what we call electrophilic substitution reactions. Essentially, we're going to substitute hydrogen on the ring for whatever our electrophile is, and so therefore it's an electrophilic substitution reaction. And so the mechanism, which we'll look at in a lot more detail in the next video, is shown below. We have our benzene ring acting as our nucleophile, it's our electron dense region. We have an electrophile, and we draw an arrow which goes from one of the double bonds. Now, sometimes you might also draw this using the ring. So if you've drawn it using double bonds, you have to have an arrow from a double bond to the electrophile. If you're drawing it using the ring, an arrow from the center of from the ring to the electrophile. Remember that arrows always go from high electron density to low electron density. This means that we've now broken, if we use this sort of double bond picture below, we've broken that double bond. Like in an electrophilic addition reaction of alkenes, the electrophile has gone onto one of the carbon atoms, and because we've broken the double bond, another of the carbon atoms is left with a positive charge, a carbocation. But remember, we said that the ring likes to remain intact in this delocalization, the aromatic, the delocalization energy, the aromaticity is really, really stable. And so the second step of this is to reform that delocalization, to reform the aromatic ring. And so we do that by simply removing the hydrogen that is on the carbon we've attached our electrophile to. So the hydrogen goes with an arrow from the CH bond, our region of electron density, to the middle of the carbon-carbon bond to show that we're forming a double bond. So, time to have a go at some questions. We need to name the following structures, and then to draw the 2 resonance structures for benzene, say which of the bonds are shorter and stronger, and to talk about whether that's really the case. So if you'd like to have a go, pause the video, and the answers will be on the next slide. So the first bit was to name the structures. So the first structure here is we have a bromine group attached, we have a chloro group attached, and we have a nitro group attached, as well as an ethyl group attached. And we need to number all of these. So we're going to use benzene as the root of our name here. So we're going to end with benzene. And then we just need to number these substituents. And remember that we always go in alphabetical order. So the bromo is going to go first, then the chloro, then the ethyl, and then the nitro. And we write it in our name. And typically the convention is that the nitro group tends to take priority and therefore tends to be the 1 substituent. And then we just kind of go around the ring. And in this case, we're going around anti-clockwise to give the lowest numbers. So this ends up being 3 bromo, 2 chloro, 5 ethyl, 1 nitrobenzene. The second example here, we have a bromo group attached, a chloro group attached, 3 methyl groups attached, and then also a carboxylic acid. So remember that there's sort of 2 special cases, were the carboxylic acid and the aldehyde. So we're going to name this either as benzene carboxylic acid or benzoic acid at the end of our name. And then we just need to, again, number the substituents and make sure they go in alphabetical order. So the bromo will go first, then the chloro, and then the methyl groups. And then we have to number them and essentially it doesn't matter which way essentially we go around this. Here I'm going to go again in an anti-clockwise direction, and so we're going to have the carboxylic acid part of it takes priority. That's carbon number 1. So this will be named as 2-bromo, 6-chloro, 3,4,5 trimethyl benzoic acid. Second question was to draw the 2 resonance structures for benzene. So remember, the resonance structures are these structures that don't actually exist. We draw a resonance arrow, a double-ended arrow. And so these are the structures that don't actually exist. So we draw our 2 what we call localized structures with the alternating double bonds and single bonds. And the 2 structures simply are just the double bonds being in different positions. Now, if this was the true case, the double bond would be shorter and stronger than the single bonds. But in reality, we know that actually the proper structure that exists is the weighted average of these 2 structures, and all bonds are exactly the same length, they're all the same strength. We talked about this idea of a more than a half bond because of the delocalization of the p orbital electrons in the benzene ring. So thank you for watching. You can find more videos like this on my YouTube channel. If you found the video helpful, please leave a review on the tuition website. I offer tuition for chemistry, so if you're interested, check out one of the tuition pages. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.